In the last part of the compression unit, we'll look at text transformations or text transforms, which are methods that don't by themselves reduce the compressed size of the text, but they help other methods pick up redundancies that were there from the beginning, but they couldn't see them. Sounds a bit curious, maybe. To motivate where this comes from, if we recap what we've seen so far, we've seen run length encoding, which can pick up runs, long repeated occurrences of the same character. We had Huffman to pick up non-uniform frequencies, and Lempel-Ziff-Welch for somewhat locally repeated substrings. But all of them can be frustratingly blind to some obvious redundancies. For example, if the repetitions are too distant, Lempel-Ziff-Welch doesn't pick them up because the dictionary is already flushed. If overall the probabilities for each of the frequencies of characters are evenly distributed, but they're more likely to be a certain character in one part and more likely to be another one in another part, it averages out and Huffman doesn't profit from it, whereas it might be profited from with a more clever regime. And this is not a hypothetical thing. This is what DNA sequences often do. There's regions where some nucleotides are much more frequent or much more likely than others, and then in other regions it's different. So overall, you can't compress a DNA sequence with Huffman much, but locally you sometimes can. But Huffman doesn't see that. And similarly for run length encoding, I mean, it's very, very greedy about the runs. If you have something that's slightly different, but still very repetitive, it doesn't see it at all. So what can we do? Well, the hero of the day for this one are these text transformations. These are functions that take text and produce text, and you can invert them. They don't by themselves reduce space, but they somehow make the redundancies more digestible. And we'll see one concrete example now in the form of the move-to-front transformation. The idea of move-to-front comes from something entirely different, namely from the idea if you want to use a singly linked list for storing a dictionary. So you have objects and you store them these as a linked list like this, right? If you want to access one of them, then you have to traverse. So you have a pointer for the first thing. You have to traverse through the list until you find the one that you were looking for. Now, that's overall not a great dictionary implementation, linear time for most elements to find them. But if you happen to find one of the early ones, if you're trying to find one of the early ones, it's very fast. So in some cases, when your accesses are very clustered, you can maybe hope that the thing you accessed before is close to the beginning. And move to front is the idea of making it so. So if you have some entries here, and you say, okay, I have an access to A, I have to follow through this, but then after I access A, I'll move this to the front. So I'll take the pointer here, point to here, and move the overhaul tail to A. So if I access A straight away again, it's at the front. If I access it without many other things in between, it will still be close to the front. So that's why it's called a self-adjusting linked list, because it automatically learns a bit which things are accessed more often. So the rule here, again, was very simple. Whenever you access something, you take that out of the list and make it the new front of the list. You move it to the front, MTF. And you can do this in linked lists by just bending pointers around. Don't think of this as an array. That's where this comes from. Now, this has nothing to do with compression, right? What we'll use here is such a self-adjusting linked list for the alphabet. Okay. So each character we can treat as an access to this list of all the characters. And then we encode the character with its index, with its offset in this list. How far did you have to travel down the list? And we keep the rule as before. So tricks me each time. All right, everyone relieved that it still works. I could have been able to tell after 10 seconds, but well. We still keep the move to front rule, so when we access a character, we move it to the front of the list. So the numbers that we associate with characters keep changing all the time. The only thing that we have to make sure is that the decoder does the same, then that's fine. So in this case, unlike what we had before, the source alphabet is arbitrary, but the coded alphabet now is integers. And again, think of this as an intermediate stage. You have to do some encoding after that anyways, so it doesn't have to go to binary straight away. We'll come back to what properties that has after the example, but first I want to make sure that the move to front rule is clear. So here's a small innocent question. If you have that as the entry of the list, let me draw it. Then you do an access to A. What does the list look like afterwards? And you should imagine access at the front. Yeah, looks good. Most people seem to be certain, and so let's not delay it for more than necessary. How does it work? We go through the list until we find our A. And we rip it out. So we take a copy. We take out our A, put it to the front, and just close the list again here. So we get A, X, Y, Z, B, C. Okay, good. That was easy enough, I hope. Because it's so easy, let's start with the code, just because it nicely shows how encoding and decoding is very, very similar in this case. In both cases, we start with our move to front list of all the alphabet symbols. And by convention, we start in alphabetic order. We have to have some convention. In the encoding step, we have the source text given, and we produce the coded text. So we go through all the letters in the source text. We find the next character. We find the position of that character in our move to front list. And that position is added to the coded text. And then we do the move to front transformation on L. And for decoding, we do the exact same, except now we're given the coded text and we produce the source text. We find the next position in the list by taking the code word. Then we get the character at that position and append that to the source text and apply a move to front. So quick example, not so much because I think you need it to understand this, but because it illustrates the properties nicely. Okay, so here's our alphabet and here's the source text. Now, how does encoding work? We find the position where the letter is, that's 8, so that's our coded thing. And now we apply move to front, right? So we take this one and put it to the front. And if we do that, see I is now here. These have all shifted over. The next letter is at that position, so it's encoded by 13. And then we take it, move it all the way to the front. So all of these will move one position right, and N goes to the front. N is here, and these have all moved. Now the next letter, again, we find where it is, store it by that number, and do move to front. I'll zoom through the rest. I think it's hopefully clear. Okay. So what you get at the end is a sequence of numbers. And on this example, I'd like to have a closer look at what the properties of this sequence of numbers could be. First of all, if you have a run of characters in S, what happens with that? So we have a very short run here, 2 Fs in a row. Well, after the first F, F is at the beginning of the list. So the second F will be a 0. Obvious, right? And if I had more Fs, then there would be more zeros. So we get zeros after the first. Now sometimes we also get these things like a run in the coded text. All these 3s. What does that mean? Well, if you look where it comes from, it meant that C at this point was at position 3 in the move to front list. And then this was at position 3, and then this was at position 3. So it means that there's another occurrence of this string somewhere earlier. And there's some letters in between that mean things are shifted over. But other than that, each of these letters just shifts the list, and we keep a constant offset as how far we look back. So there's somehow a repetition in S that leads to something like a very monotone sequence in the coded text. So these are at least hints that something becomes more compressible in this via this process. Okay, so if you look at it, move to front itself doesn't really compress the text, depending on how we store things. But if you use some fixed code, again, we would have to specify how we encode the code words here. What happens intuitively, and I hope the 2 examples in the questions from the example hint to that, is if you have something with low empirical entropy locally, so there's a region in the text, in the source text, where you have only some characters occurring, but these characters can change over the different portions of the text. Then move to front transforms that to a globally low empirical entropy. Remember, empirical entropy was this: we take the frequencies of letters and take the entropy of that. We covered that yesterday a bit. And that means low entropy means Huffman works well. And so move to front is somehow able to take changing but low entropy parts in the text and transform them in globally low entropy on those numbers. And so via that vehicle, it makes Huffman more effective. If we want to store the numbers, we can also use gamma code, but Huffman will usually be better. There's a tendency in the move to front output to have small numbers if that is the case. Now, the property that MTF has is great, but it turns out that at least English text doesn't actually have these locally low empirical entropies. I mentioned DNA data sometimes has, so that there it works directly to some degree, but many types of texts don't have this. But it turns out we have another transform coming up that helps there, but we'll have to delay that. And the way it works in the end will be another transformation, the Burris-Wheeler transform, creates such low local entropy MTF transforms that into low global entropy, and then we can apply Huffman at the end.